I'm going to strongly encourage you during this unit to have your formula sheet in front of you. And the reason is, if you look at the electrostatics section, which is right here, in fact, I'm going to zoom in here. The problem is, a lot of these equations look very similar. Here I have F equals K Q1 Q2 over R squared. Here I have E equals K Q over R squared. Here I have E equals K Q1 Q2 over R. Here I have V equals K Q over R. And so one of the strategies you actually want to do is almost train your eyes to look at the right place for the right equation when it's in your mind, so you don't get these mixed up. The by far biggest mistake we have, the biggest foible on this test when we get there, kids find the wrong thing because all the equations look alike. And the problem is, if I'm giving you 7 marks to find the voltage and you chose to find the electric potential energy with the wrong equation, I have to give you 0. I can't even give you any part marks, because that's like I said, find the acceleration, and you chose to find the distance. I'm sorry, I can't even start to give you any part marks anywhere. You found the completely wrong thing. So you want to keep your formula sheet handy. Also, we did add one thing, Nevada and whoever else was away, I think we put absolute value signs around that right there, I think. Yes? While you're at it, you can put an absolute value sign around that Q there. None of the other Qs. Let me show you that on the actual formula sheet. Mr. Duick, formula sheet, right here. Electrostatics. So you can put an absolute value sign right there, and you can put an absolute value sign right there.
Students, just
let me just pause this. Hang on a second here.
Some of you that had expressed
Pause.
concern to the office.
There are going to be, Brendan, sometimes in electricity when we want to include the positives or the negatives, and there are going to be sometimes in electricity when we just want to ignore the not positive and negatives, when instead we're going to use, are you ready? Are you ready? Are you ready? Instead, we're going to use like, unlike, attract. Okay? So we left off right here. We had just finished doing something like example 4. I like example 4. I like example 4. Example 4 is a nice question. What I mean by that is finding the force on one charge when you have 3 or more charges in the picture, when you have to go 2 charges at a time and then add the forces vectorially. We were using Coulomb's law. Some quick reviews. We said charge is measured in coulombs. In fact, you may have noticed this formula, this equation, looks mathematically an awful lot like which other equation that we just finished looking at? It looks like universal gravitation, and this has sparked physicists for quite some time. We have said, well, look, if charge comes in positive and negative varieties, why doesn't mass? Is there a mass that would repel rather than attract gravity? I mean, they sure look symmetrical mathematically. Instead of big G, you got K, 9 times 10 to the 9th. Instead of masses, you got charges and coulombs, but it sure does look similar. All right. Oh, we also talked about the fact that most of the time we'll be using microcoulombs. I think I said to you, 1 coulomb of charge is massive, is huge. You would not want to absorb that all at once. Pause here. So here's a little thought experiment. It says this: at what point could we place a positive 1 microcoulomb charge? You know what? I don't care about the magnitude, Kayla. I just care that it's positive, so that it would experience no net force. We're going to figure that out by using like, unlike. Okay? I'm going to start out, I think, looking at location A and location E. I have 2 charges in this picture. We can't deal with 2 charges at once. Instead, we're going to use, here's our fancy word, the principle of superposition. What that really means is temporarily we're going to pretend that charge isn't there and ask what charge the first charge. You know what? Let's call this charge 1. Let's call this charge 2. We'll ask what charge 1 is doing, then we'll ask what charge 2 is doing, then we'll add up those two consequences. Okay? So, I'd like you to imagine that there was a little positive charge sitting at location A. Charge 1, negative or positive? Negative. So will charge 1 repel or attract that positive charge at location A? Attract. Let's draw a force pointing that way. Attract. Charge 2, negative or positive? So will charge 2 repel or attract? Will charge 2 repel or attract a positive charge right there? Ignore this one, just looking at charge 2. It's also going to attract. Can to the right plus to the right possibly give you 0 force as an answer? No. So, can't be correct. You okay with that, James? A force to the right plus a force to the right can't possibly be 0. Newton's first is going to kick in. You must have an unbalanced force. Let's do the same with location E. Let's imagine a little positive test charge right here. And let's look at charge 2. Charge 2 is negative. Charge 1 is positive. Will charge 2 attract or repel our little positive test charge? Attract. So there's going to be a force to the left right there from charge 2. What about from charge 1? Correct. So can left plus, and on cue Sarah yawned as well, and now Brendan's yawning. Stop it, or I'll deal with it. Can left plus left possibly be 0? In fact, I have a feeling it's going to be B or D, somewhere in between, but let's tackle those last. Let's first deal with charge C. Let's put a little positive charge right there. Which way will that positive charge feel a force from charge 1? Are they like or are they unlike? They're unlike. One's negative, one's positive. So unlike charges attract. So there's going to be a force in that direction. You know what? I'm going to make that arrow a bit longer, and you'll see why in just a second. Now Simone's yawning. Really? See what you did, Connor? What about charge 2? Robbie's covering it up. What about charge 2? Well, I think it's also going to be attracted, but is charge 2 closer or further away? But is charge 2 bigger or smaller? Yeah, okay. You know what? It may be about the same size. Are those two forces at angles to each other? Liam, did I say angles? Why? I'm going to add them. Okay, so this would give me a force. I'm going to draw it up here. That plus that. I get something kind of like that. I just know I don't get 0. There is still a net unbalanced force. So let's put a big X through location C. B or D? Which one? Why B and not D? Let's look at location D. Let's put a little positive test charge there. Which way will charge 2 be exerting a force on it? Towards to the right or repel to the left? Towards to the right. Are we closer to charge 2 or are we which way will charge 1 be exerting a force on it? Towards to the left or repel to the right? Towards to the left. So these are going to be having a little tug of war right here. It's going to get pulled this way and it's going to get pulled this way. Which charge is bigger, charge 1 or charge 2? Charge 2. Which charge is closer, charge 1 or charge 2? Which is going to exert a bigger force? Here, I think you're going to have charge 2 exerting a really big force and charge 1 exerting a tiny force. Really big to the right plus tiny to the left also still doesn't cancel out. Now let's look at location B. If we put a little positive test charge right there, it is going to get tugged to the left by charge 1. It's also going to get tugged to the right by charge 1. Oh, but we're further, to the right by charge 2, but we're further away from charge 2, so it'll be smaller. Oh, but charge 2 is bigger, so it'll be bigger. I suspect right around there, you'll have an equilibrium point where the two tugs are identical and where your net force is 0. Okay? You know what? I didn't say so in the question. Typically, you'll see me say something like where the two fixed charges, and that's like you can imagine they're thumbtacked to your paper, or little invisible angels are holding them in place, or whatever you want to do, but they're not free to move. Okay? It says explain your answer. I would answer it with those diagrams that I've just done, I think. You could probably explain it in English, but I would do that. Julie, that wasn't too hideous because most of the forces were still in a straight line, aside from location C. And as a written question, I will give you the forces in a straight line, like example 4. But as a nasty multiple choice question, something like example 5 would be fair game. Although this isn't going to be too hideous because I think it's going to be a lovely right angle. I don't think I'm going to have to pull out sine law and cosine law. I think I'm going to be able to use SOHCAHTOA trig. But I'm pretty sure I'm going to be using SOHCAHTOA trig just by looking at the picture, James. As soon as I see that, I go, oh, we got angles. Okay? It wants me to find the electrical force and direction on the electron as shown below. The electron is right there. I'm going to call the electron charge 1. I'll call this charge 2. I'll call this charge 3. Robbie V, what does this want me to find the force on? Because there's 3 charges. You need to tell me which charge I'm focusing on. Read care. Oh, yeah, the electron. Okay, so here's how I'm going to do this. I'm going to find the force from charge 2 on charge 1, magnitude and direction. I'm going to find the force from charge 3 on charge 1, magnitude and direction, and then I'm going to add them vectorially. Only in this case, I'll probably have to add them tip to tail vectorially instead of just being able to go winner minus loser. How do I find forces? It's going to be K, Q2, Q1 over R between 2 and 1 squared. By the way, you could also write 1, 2 and 1 and 2 because when you're multiplying, the order doesn't matter. It's going to be K, Q3, Q1 over the distance between location 3 and 1 squared. K is 9 times 10 to the 9th. That's on your formula sheet, but that one you'll probably memorize because it's a lovely constant. How big is charge 2? 2 microcoulombs. Isn't it negative 2, Mr. Dewick? No, we're going to use, ready, Drake? Like, unlike. So we're not going to put positive and negatives in. We'll figure out the direction ourselves. How big is charge 1? It's an electron. And I'm saying that with as much scorn and disdain in my voice to tell you, look it up. 1.6 times 10 to the negative 19. That's the elementary charge on your sheet. Divided by 2 micrometers as well. Yes? So 2 times 10 to the negative 6 squared. How big is the force between charge 2 and charge 1? Well, really the force from charge 2 on charge 1. It might be worth practicing on your calculator. I don't know. Do you get 7.2 times 10 to the negative 4? Okay. So 7.2 times 10 to the negative 4 newtons, and now we come to the really important part, direction. Which way is that electron feeling a force from charge 2? go to the right, you call it east, whatever. Okay? I'm going to use this for later, so I'll put a box around it. What about if I want to find the force from charge 3 on that electron? It's going to be 9 times 10 to the 9th. Charge 3 looks like it's 1 microcoulomb. Charge 1, it's an electron. 1.6 times 10 to the negative 19 divided by, and this is also 2 micrometers. Don't forget the squared. Actually, Sarah, this is kind of nice. If I'm lucky, I think I can just backspace and edit, and all I'm changing is that 2 to a 1. And I get 3.6 times 10 to negative 4 newtons. The force from charge 3 on charge 1 is 3.6 times 10 to the negative 4 newtons. And now here's the important part. Direction. Which way is that electron feeling a force from charge 1? Down or south? Those are my 2 components. I'm going to add them vectorially. Is that okay, Brendan? So now, let's do a little tip to tail. I have to the right, and that's 7.2 times 10 to the negative 4. Down. I know that 3.6 is half as... Am I wrong somewhere?
Can I ask a question?
Yeah.
Are electrons negative, right? Is that thing?
Yeah.
Would it repel from the first?
Ah, someone said to the right. Shouldn't this first one here be to the left? So who said to the right? They weren't right. Whoever said and called that out, whoops. Is that why you were looking all confused?
Yeah.
You should have been. So I got to fix my vector diagram. It's going to look like this. To the left, 7.2 times 10 to the negative 4 plus down, and the down value is 3.6 times 10 to the negative 4. Here is my resultant. This is what the question wants me to find. So let me again say, I'm not going to give you one this tricky as a written question. I would have no problem as a multiple choice, make you really think about it. It's good review of vectors and tip to tail and all that stuff. Thankfully, I think I can use straight Pythagoras. Is that wrong still? No?
No, you're right.
So let's go. F is going to be 3.6 times 10 to the negative 4 squared plus 7.2 times 10 to the negative 4 squared equals square root of that. Has a magnitude of 8.05 times 10 to the negative 4. Did they only ask for the magnitude, or did they also ask for the direction in the question?
Direction.
Okay. Am I going to put theta in the bottom left corner or in the top right corner?
Right.
Okay, it's always where I'm coming from. There's theta. This 7.2 adjacent, yes. This 3.6 opposite. Which trig function? Tan. So I can go tan theta equals opposite over adjacent. Make sure you're in degrees. There will be some trig in this unit occasionally, so those of you that are in math and in radians, or in calculus and in radians, make sure you're in degrees. I get a theta of 26.6 degrees. No? Am I wrong? I think I'm right. Am I not? Yeah. You know what? Let's throw a little compass rose on here. North, east, south, west. So that theta right there, north of south, east of west, what of what?
Southwest.
Okay. That question has some real teeth, and it has some length to it. Lots of writing and lots of places to make mistakes, but point being, you know what? Forces still behave the same way. Go west first, right, Sarah, and then go south of west. Turn the page. Oh! That's it? So, questions from the homework for you to work on. Number 1 is good. Two is good. Three, no. 4, no. 5 is fine. 7 is good. Skip 6. 8 is good. 9 is good. 11 is good. What happened to number 10? I don't know. 14 is good. By the way, both in number 9 and number 14, you ready? What path is this electron tracing out? What force is pulling it in a circle? Not gravity. Here, for our Bohr model of an electron, of an atom, we can say electrical force is what's pulling me in a circle. And all of the same stuff we're able to find periods and radiuses and velocities and speeds can be done now.